Imagine a job interview conducted as a knife fight in a public square. In 16th century Italy, university positions in mathematics were not secure. A man holding a lectureship could be challenged by an outsider, and the challenge took a formal shape. Each party drew up a list of problems, 30 was a common number, and deposited it with a notary, along with a sum of money. A deadline was set, usually a month or two. Whoever solved more of his opponent's problems won, the money, the reputation, and often the post. These were public events. Crowds came. The verdict was announced, printed, and gossiped about across the peninsula, and a man who lost badly might find his lecture hall empty the following term. Now think about what that arrangement does to knowledge. If you have discovered a method nobody else possesses, it is not merely an achievement. It is a weapon, and its value depends entirely on nobody else having it. Publish, and you have armed every rival in Italy. Keep it quiet, and you can win contests for the rest of your life, choosing problems that only your secret can crack while your opponents flail. So they kept quiet. The great mathematical discovery of the Italian Renaissance was made in about 1515 and stayed hidden for 30 years, passed by deathbed confidence and extracted under oath. And it emerged at last only because one man broke a promise in a way that has been argued about for 470 years. And when it emerged, it brought something with it that nobody had asked for and nobody wanted. A number that could not exist. The thing they were all chasing was the cubic. Remember where the problem stood at the end of chapter 10? The quadratic? Equations involving the square of an unknown had been fully solved in Baghdad 7 centuries earlier. The cubic, one step up, had defeated everybody. Omar Khayyam had built a magnificent workaround, catching the roots geometrically with intersecting curves, and had stated plainly that he could not find an arithmetical solution and hoped somebody after him would. Nobody had. Luca Pacioli, whose great printed compendium we met at the end of chapter 9, had declared in 1494 that solving the cubic was as hopeless as squaring the circle. That was the settled professional opinion. This problem is beyond us. It was solved about 20 years later by a professor at Bologna named Scipione del Ferro. We know almost nothing about how. He did not publish it, did not lecture on it, did not tell his colleagues. On his deathbed in 1526, he passed it to a student named Antonio Maria Fire, and he left it written in a private notebook that went to his son-in-law. That is the entire fate of the first solution to a 2,000-year-old problem. One deathbed whisper and a notebook in a drawer. Fire was not a first-rate mathematician, but he now owned a first-rate weapon, and in 1535 he decided to use it. He challenged a mathematics teacher in Venice named Niccolò Tartaglia. Tartaglia is one of the more remarkable people in this book, and his name is a wound. He was born Niccolò Fontana in Brescia-Por around 1500. In 1512, a French army sacked the city, and in the massacre a soldier struck the boy across the face with a saber, cutting through his jaw and palate. He was about 12. He survived, his family could not afford a doctor, and he later wrote that his mother tended the wounds herself, and he was left with a speech impediment so pronounced that people called him Tartaglia, the stammerer. He took the insult and made it his surname. He wore a beard for the rest of his life to cover the scars. He never had formal schooling in mathematics. He taught himself and then taught others in Verona and Venice, scraping a living from private pupils and from consulting work on gunnery for the Venetian arsenal. That consulting produced something worth pausing on. In 1537, he published the first serious scientific study of the flight of cannonballs, arguing against the received view that a projectile flies straight and then drops, and insisting the path is curved throughout. He also, at one point, expressed real misgivings about the whole enterprise, the sense that refining the art of killing was not an honorable use of a mind, and then published anyway. He needed the work. It is one of the earliest recorded flinches of a scientist's conscience, and it did not stop him, which is also part of the pattern. When Fire's challenge arrived, Tartaglia had been claiming publicly that he could solve certain cubics. Fire, holding Del Ferro's secret, set him 30 problems of exactly the type he knew the secret handled, expecting an easy kill. Tartaglia could not do them. The deadline approached. And then, in the small hours of a February night in 1535, days before time ran out, he found it, the method, worked out from nothing under the pressure of imminent public humiliation. He solved all 30 of Fire's problems in about 2 hours. Fire solved essentially none of his. Tartaglia declined the prize, which was 30 banquets, and the gesture cost him nothing and bought him a great deal. He now had the most valuable secret in European mathematics, and he had every intention of keeping it. Enter Gerolamo Cardano, who is the most extravagantly complicated human being we have met so far. He was born in Pavia in 1501, the illegitimate son of a Milanese lawyer who was also a serious geometer, good enough that Leonardo da Vinci consulted him about problems. Illegitimacy shaped Cardano's whole early career. The College of Physicians in Milan refused him admission repeatedly on those grounds, and he spent years practicing medicine in provincial towns, gambling to pay for food and burning with the conviction that he was better than his circumstances. He was, as it turned out, right. He became one of the most celebrated physicians in Europe. He was summoned to Scotland to treat the Archbishop of St. Andrews for a crippling asthma nobody else could touch, and cured him by, among other things, getting rid of the feather bedding, which is arguably the first recorded diagnosis of an allergy. He wrote constantly on everything: medicine, natural philosophy, mechanics, astrology, morals, dreams, consolation, his own life. Something over 200 works. He also wrote the first genuinely mathematical treatment of gambling odds, an analysis of dice and card games, by a man who played compulsively and understood, better than anyone alive, that chance had a structure. He never published it. It sat in his papers for nearly a century after his death, which is why the birth of probability in Chapter 13 belongs to 2 Frenchmen writing letters, and not to a Milanese physician who got there first and told no one. His life also went spectacularly, unbearably wrong. His elder son was tried and executed in 1560 for poisoning his wife, and Cardano, who had exhausted himself trying to save him, wrote about it afterward with a rawness that is difficult to read. His younger son was a thief who robbed him, and whom he eventually had banished. In 1570, he was arrested by the Inquisition, apparently over having cast a horoscope of Christ, spent time in prison, recanted, and was released. He then moved to Rome and was granted a pension by the Pope, which tells you something about the 16th century. This is the man who, in 1539, wrote to Tartaglia. The approach was smooth. Cardano was preparing an arithmetic book and asked politely whether Tartaglia would allow the cubic method to be included, with full credit. Tartaglia refused. Cardano tried again with a better lure. He was well connected in Milan, and he dangled an introduction to the Spanish governor, patronage, security, an end to scraping a living from pupils. Tartaglia, who was poor and knew exactly what patronage was worth, came to Milan. On March 25, 1539, in Cardano's house, he handed it over. He did not hand over a proof or a clear explanation. He handed over a poem, 25 lines of Italian verse, in tercets, encoding the rule in language dense enough that you would need to already half understand it to follow. Verse as encryption, and also verse as memory aid. The same reason Indian mathematicians wrote their arithmetic in Sanskrit meter in Chapter 7. And Cardano swore an oath. By Tartaglia's account, he swore on the Gospels, as a Christian gentleman, never to publish the method, and further to write it down only in cipher, so that after his death, nobody would be able to read it. Then Tartaglia went home. The introduction to the governor did not materialize. What happened next is where the story stops being simple. Cardano set to work on the method with his servant, a young man named Lodovico Ferrari, who had come into the household as a boy and turned out to be a mathematical prodigy. Cardano educated him. Ferrari became his student, his collaborator, and his fiercely loyal attack dog. Between them, in a few years, they did something enormous. They worked out how to handle all the cases of the cubic, not just the one Tartaglia's poem covered, which required, incidentally, confronting negative numbers, since a general treatment cannot avoid them. And then Ferrari, who was in his early 20s, solved the quartic, the 4th-degree equation, the next rung up, which nobody had touched at all. That is a spectacular result. and Cardano could not print a word of it. Because Ferrari's method for the quartic works by reducing it to a cubic, you crack the fourth degree by turning it into a third-degree problem and solving that. So publishing Ferrari's discovery meant publishing the cubic solution, and the cubic solution was under oath. For several years they sat on it, a brilliant young man's masterpiece locked in a drawer by a promise his teacher had made to a stranger. Then, in 1543, Cardano and Ferrari traveled to Bologna and called on Annibale della Nave, Scipione del Ferro's son-in-law, and the keeper of his papers. Della Nave showed them the notebook. And there it was, in Del Ferro's own hand. The solution, worked out at least 20 years before Tartaglia's night of desperation, entirely independently. Cardano decided this changed everything. The thing he had sworn not to publish was Tartaglia's discovery, and Tartaglia's discovery turned out to be a rediscovery. What he would publish was Del Ferro's. Whether that reasoning is honorable or self-serving is a question I will leave with you. What I will say is that it is not nothing. The priority claim genuinely was false, and Cardano genuinely had seen the earlier manuscript. In 1545, he published the Ars Magna, a great art, and it is one of the most important mathematics books ever printed. It contains the solution of the cubic in every case. It contains Ferrari's solution of the quartic. It handles negative numbers more openly than any European work before it. And it names names. Cardano writes that Scipione del Ferro discovered the rule first, that Tartaglia, in a competition with del Ferro's pupil, found it again, that Tartaglia gave it to him at his entreaty, and that Ferrari, his former pupil, solved the fourth degree. He does not claim the discovery. He credits everyone in order in print. This matters more than it might seem, and it is worth stopping on. In a culture where methods were weapons and secrecy was the rational strategy, Cardano published a complete account of the strongest results in the field, and attributed each one to whoever had actually found it. That is the norm we now call citation, and the Ars Magna is one of the places you can watch it being born, not out of virtue, particularly, but because a man wanted to publish something he half-owned, and could only do it by being scrupulous about the parts he didn't. Tartaglia did not see it that way. He saw an oath broken by a wealthy, well-connected physician who had lured him to Milan under false pretenses, and then used his life's discovery to make a name. In 1546, he published his own account, including the text of the oath, and attacked Cardano in the strongest terms he could print. Cardano, who was famous and busy and had a talent for not engaging, said nothing. Ferrari answered instead. Over about 18 months, 12 printed pamphlets flew back and forth between Ferrari in Milan and Tartaglia in Venice, public, vicious, and widely read. The 16th century equivalent of a feud conducted entirely in open letters. It ended in a church garden in Milan on August 10, 1548, before a large and partisan crowd. Ferrari and Tartaglia met in person to debate. It went badly for Tartaglia. Ferrari was 26, brilliant, and knew the full general theory, including the quartic, including the cases Tartaglia had never worked out. While Tartaglia's mastery stopped at the method he had found in one desperate night 13 years earlier. The audience was Milanese and Ferrari was the local man. Tartaglia left before the contest was finished, and afterward blamed the hostility of the crowd. He lost a lectureship he had just obtained in Brescia. He returned to Venice, where he died in 1557, poor. Ferrari, on the winning side, was showered with offers, took a lucrative position, and died in 1565 at 43. There is a persistent story that his sister poisoned him for the inheritance, which appears in the sources and cannot be verified. And the formula, to this day, is called Cardano's. So much for the men. Now the mathematics and the monster. Here is what the formula does. Take a cubic in the standard reduced form. A cube of the unknown plus some multiple of the unknown equals a number. The recipe tells you to combine those two given numbers in a particular way. Take a square root of the result, then take cube roots of two quantities built from it and add them. Out comes the answer. It works. It is a genuine general solution to a problem that had stood since Babylon, and it is the first major advance on Greek mathematics that Europe could claim as its own. But look at the middle step. There is a square root in there, and it is the square root of a quantity that can perfectly well come out negative. Every schoolchild knows what that means. A positive number times itself is positive. A negative number times itself is also positive. That was Brahmagupta's rule from chapter 7, debt times debt makes fortune. So there is no number anywhere whose square is negative. The operation is not difficult. It is impossible, in exactly the sense that the diagonal of the square had no ratio. And here it sits, in the middle of a formula that otherwise works perfectly. Now for the part that makes this unavoidable rather than merely awkward, and it is the deepest irony in the chapter. You might reasonably expect the impossible square root to show up when the equation has no sensible answer, a signal that you have asked a bad question. The way a negative answer to a length problem told Al-Khwarizmi to throw the case out. It is exactly the reverse. The formula sails through smoothly when the cubic has only one real solution. The square root goes negative precisely when the equation has three perfectly good, ordinary, real solutions. The case where the answer is most abundantly, unambiguously real is the case where the only route to it runs through a quantity that does not exist. Mathematicians later gave this the name Casus Irreducibilis, the irreducible case, and in the 19th century it was proved that there is no way around it. You cannot rewrite the formula cleverly to avoid the impossible step. For those cubics, every root from the coefficients to the roots, using only ordinary arithmetic and roots of real numbers, is closed. The only door is the one that isn't there. That is a genuinely startling thing about the universe of number. Not here is a strange object we might optionally admit, but the impossible object is load-bearing. Refuse it and you cannot get to answers that are indisputably real. Cardano met the thing head-on in the Ars Magna and recoiled. He poses a small puzzle. Divide 10 into two parts whose product is 40. Try it with ordinary numbers and you fail. The best you can do with two parts summing to 10 is a product of 25, so 40 is out of reach. The problem has no solution. Cardano works it anyway and gets two answers, 5 plus the square root of negative 15, and 5 minus the square root of negative 15. Then he checks them. Add them together and the roots cancel. You get 10. Multiply them, and by the ordinary rules of multiplication, you get 25 minus the square of the square root of negative 15, which is 25 minus negative 15, which is 40. Both conditions satisfied. By two quantities that cannot exist. Cardano's own reaction in the text is somewhere between fascination and disgust. He describes the mental contortion required to entertain such things, and concludes that the whole business is as subtle as it is useless. He puts it down and moves on. You can hardly blame him. He had followed the arithmetic into a place where the rules kept working after the objects stopped making sense, and he had no framework whatsoever for what that meant. The man who did something about it was an engineer. Rafael Bombelli was born in Bologna in 1526 and spent his working life reclaiming marshland, draining the Val di Chiana for a papal patron, a long, muddy, practical job involving surveying and hydraulics. During a suspension of the works, with time on his hands, he wrote a book on algebra. It came out in 1572, the year he died. Bombelli went after the case that had stopped Cardano, and he chose an example so pointed it amounts to an argument. Take the equation. The cube of a number equals 15 times that number plus 4. You can find the answer by inspection. Try 4. 4 cubed is 64, and 15 fours plus 4 is 64. It works. The answer is 4. A whole number. No mystery, no subtlety, nothing exotic, the sort of solution you could get a child to guess. Now run Cardano's formula on it. The square root goes negative. And the formula tells you that the answer is the sum of the cube root of 2 plus the square root of negative 121, and the cube root of 2 minus the square root of negative 121. That is the situation in miniature, and it is absurd. The answer is 4. And the general method, the great achievement of the age, correct in every other case, insists on routing you through two monstrous expressions built out of the square root of a negative number. Most people would conclude the formula had broken. Bombelli concluded something else. He called it a wild thought. What if, he wondered, those two grotesque cube roots are themselves quantities of the same kind, each one an ordinary number with a little impossible piece attached? And what if, when you add them, the impossible pieces cancel each other out and leave something perfectly ordinary behind? So he guessed. Suppose the first cube root is 2 plus the square root of -1, and the second is 2 minus it. Add them, the impossible halves annihilate, and you are left with 4, which is the right answer. But a guess is not mathematics, so he checked it by cubing. Take 2 plus the square root of -1 and multiply it out 3 times, following the ordinary rules of algebra and using only one new fact, that the square root of -1 multiplied by itself gives -1. That is not an assumption about what the thing is. It is just the definition of a square root applied to a quantity we are pretending exists. Grind through the multiplication and the terms sort themselves into 2 piles, ordinary pieces and impossible pieces. And when the dust settles, you get exactly 2 plus the square root of -121, which is what the formula said it should be. It fits. The wild thought is verified. I want to be clear about what Bombelli has done, because it is the move that gets repeated for the rest of this book. He has not explained what the square root of -1 is. He has no idea. Nobody will have a satisfying answer for another 250 years. When Gauss and others realize these quantities can be understood as points on a plane, and the whole thing becomes as concrete as a map. What he has done is give them laws. In his book, he sets out how to add, subtract, and multiply these quantities, states the sign rules for combining them, and gives them names in Italian so they can be spoken about at all. He treats them as objects with fixed behavior, and he verifies that the behavior is consistent. Look back at how every monster in this book has been tamed, and you will find the same sequence. Brahmagupta did not explain the metaphysics of nothingness. He wrote down what 0 does when you add it. The Chinese did not justify quantities less than nothing. They specified how red rods and black rods combine. Eudoxus could not say what an irrational magnitude is. He gave a rule for when 2 ratios are equal and got on with it. You domesticate a monster by writing its rules, not by understanding its nature. Understanding comes later, sometimes centuries later, and it comes to people who have grown up using the thing and can no longer remember why anyone found it frightening. And notice what these quantities did for Bombelli. They were not the answer to anything. They appeared in the middle of a calculation, did their work, and vanished before the end. He went out through the impossible and came back with an ordinary whole number in his hand. The monster was a bridge, a stretch of road over territory where no numbers live, connecting 2 perfectly solid banks. That is why they got admitted. Not because anyone believed in them. Because you could get somewhere on them. The name came from Descartes, who is in the next chapter, and he did not mean it kindly. Writing in 1637, he distinguished between the roots of an equation that are real and those that are merely imaginary, quantities you can conceive of but not point to. He meant the word roughly as we mean it when we say a child has an imaginary friend. It stuck, which is a shame because it has been misleading students ever since. There is nothing more imaginary about the square root of -1 than about the square root of 2, and the diagonal of a square in Chapter 3 got called unspeakable for precisely the same reason. It was a legitimate quantity that a particular generation's number system could not name. Both names are fossils of somebody's discomfort. Euler eventually gave the thing its symbol, the letter I. Gauss gave it a geometry and coined the term we now prefer, complex numbers, for quantities with a real part and an imaginary part, of exactly the form Bombelli was writing down in 1572. That story belongs to part 4. Here is where it ended up. Complex numbers turned out to be not a curiosity, but the natural home of enormous parts of mathematics and physics. Rotation, oscillation, and wave motion are described far more elegantly with them than without. The mathematics of anything that goes round and round or back and forth is complex arithmetic in disguise. So they are the working language of electrical engineering. Every analysis of alternating current, the electricity in the wall behind you, runs on complex numbers. because the relationship between voltage and current in a circuit with coils and capacitors is exactly the kind of rotating relationship they were made for. Signal processing runs on them. Every compressed audio file, every digital image, every radio transmission passes through a transform that decomposes a signal into rotating components, and the rotations are complex numbers. And then there is quantum mechanics, which is the strangest part. The fundamental equation governing the behavior of matter at small scales has the square root of -1 sitting in it, not as a convenience but as an ineradicable feature. The state of a quantum system is described by complex quantities, and the interference between them, the reason particles behave like waves, is a consequence of their arithmetic. The universe, at its foundations, appears to be doing bookkeeping in numbers that Cardano called useless and Descartes called imaginary. A quantity that does not exist, thrown off as waste from an equation-solving formula discovered by an engineer draining a marsh, is now the notation in which physical reality is written. The impossible made ordinary. It keeps happening, and it never gets less remarkable. Next comes the man who coined the insult, and he has considerably more to answer for than that. In 1637, Descartes published a short appendix to a philosophical treatise in which he did something that changed the shape of mathematics permanently. He drew two lines at right angles and showed that every curve in geometry could be written as an equation, and every equation could be drawn as a curve. Geometry and algebra had been separate provinces since the Greeks walled them apart in Chapter 3. He tore down the wall.